All right, so welcome everyone. This is the first weekly review of the spring 2021 semester for OChem 2. And my name is Sri, and I am a peer tutor with the Student Success Center and peer tutoring. And every week on Monday through at 4 to 5:15, I will go over whatever you guys have covered in lecture the previous week. And because we are on a Monday, my reviews on a Monday, and then usually exams are on Wednesdays. He'll give it's a good time to have a weekly review. Anything you covered, self-studied over the weekend, you could come to my weekly review with questions, or just as a refresher for the next week as well as the previous week. So today we are starting with IR. This first unit, to give you guys a brief summary of this first unit before we get to that. So make sure you're in the right place, watching the right video. So it's the weekly review of Chem 23-25. And my name is Sri. And then so today we'll be talking about IR, or rather this week. Okay. And then to give you a summary of how OChem 2 is compared to OChem 1, OChem 1, there were a lot of unique conceptual material, especially in Unit 1. Unit 2 had those four mechanisms, SN1, SN2, E1, E2. And then Unit 3, which you guys don't have an exam for, had a lot of reactions regarding double bonds, triple bonds, and alcohols, right? So Unit 3 of OChem 1 is going to be how OChem 2 is, with lots of reactions. In OChem 2, every unit has both conceptual material as well as tons of reactions, okay? Unit 1 of OChem 2, this unit, you mainly deal with spectroscopy material, and what that means is these are puzzle pieces, chemistry puzzle pieces that you use to put together a certain chemistry structure, okay? Now IR, mass spec, and NMR, you will end up having to use all three puzzle tools to solve a problem. And sometimes these problems have multiple parts to it, like a reaction map, and etc. And each of these spectroscopy tools will offer unique details about the structure. And in the following weeks, you will learn what each of them do and how to best utilize them and how to solve problems with them. Okay, so that's a general overview of this unit. I'll talk about the other units when we get to them. So this week we're going to start off with IR, okay? And IRs Purpose, okay? So let me write this down. IR's main purpose, or rather, the main purpose of its functionality is it helps find functional groups. Okay. Now you guys probably have already learned this in the past week of lectures, your first two classes. But yeah, IR is mainly used to find functional groups. And if you remember, functional groups are your alkenes, alkynes, your carbonyls, ketones, carboxylic acids, triple bonds, all of those. And that is important. Each functional group has a unique energy that it bends at, and those numbers will also be important when identifying and reading the graph. So let me give you an example. So your graph might look something like this. And this is, let's assume right here is the fingerprint region, okay? And the reason why we call it the fingerprint region is because we don't really care about these, because it's really hard to tell, and it's really hard to distinguish those energies between two functional groups. And just like fingerprints, no two fingerprints are identical. That's the same way in functional groups. So you can just ignore everything that's on the right side of the fingerprint region. Okay. Now the first important point that you start out at is around 1600. Okay. Next 1600 is the energy level of a benzene ring. Okay. So this is how the graph will look like, and they'll have values at the bottom, and then at the top is where spikes and curves come from. Okay, so let me just give you an example of what that might look like. So something like this, okay? And if you see, there are sharp peaks and broad peaks, and we'll learn about the differences of that. You will mainly deal with sharp peaks because that's majority of the functional groups. Broad peaks are only reserved for two specific things, specific functional groups. It's used for, so we'll talk about alcohol, OH. OH peak is very broad, and that's what it looks like. We'll talk about the number OH is at later. And then the second broad peak is carboxylic acid. And then that is denoted as COOH. But the difference between carboxylic acid and alcohol is carboxylic acid is more wide. It's sort of like a upside down mountain. And it's kind of spiky at the bottom, okay? Sometimes people call this like a beard. It looks like a beard. Or if you wanna, I like the upside down mountain. Okay. And then you can think of this as, yeah, OH is just more smoother, and carboxylic acid is more bumpy and rough at the bottom. Okay, but both are very wide in length, or sorry, width, whereas these other three are narrow in its width. Okay, so those are very distinguishable functional groups, and OH is going to be at 3300. So let me write that down. So roughly around 3300 or 3300. And then carboxylic acid can range, because it's very wide and occupies a large area, will be anywhere from 3,000 to 3,400. But for these two, I think the number matters less compared to the shape, because you'll recognize the shape a lot quicker than you'll recognize the numbers and ranges. Okay. And the reason why I'm telling you guys this is because it's, like I said, it's a puzzle. So you have to recognize certain patterns to save time when you're taking your exam or quiz, because puzzles, as you know, can take a while, and if you're spending too much time trying to figure it out, you'll end up not finishing on time. So that's why you have to use these tips and tricks to solve the question faster. Okay. So next thing I want to talk about is the triple bonds. Specifically carbon, so I'm gonna have to write this down, but I think alkyne is just a better word. Or yeah, let me actually draw it out. Okay. So C triple bond to C, just a normal alkyne, compared to C triple bond to nitrogen, and this is called a cyanide. These also have unique like specific ranges, not necessarily the shape of the peak, but the ranges are what you want to know, and like another aspect of knowing spectroscopy is learning how to group, because there's a lot of material and a lot of numbers, so it could get very confusing. So the OH, COOH, that's one group. The triple bonds are a second group. So these ones are around the 2200 range, and C triple bond C is less than 2200, and C triple bond nitrogen is going to be greater than 2200. Okay? And then I can show this on a graph. So on a graph, let's say this is 2200. And let's say this is the top. Let's say there is a peak right here, and there is a peak right here. Okay? But it doesn't necessarily tell you what that number is, or right here. I mean, sometimes they will. Sometimes you have to visually see on the graph where it's located. So clearly you can see that one is below 2200, one is past 2200. Okay. So that should tell you which one's which. This is the alkyne. This is the cyanide. Okay. Obviously, more often than not, only one of these will exist. So if only this one is here, make sure you look at the 2200 range and then be like, okay, it's past 2200, it's probably like 2300, 2250, something like that. There's probably, my structure contains a C triple bond nitrogen somewhere, okay? All right, so we're done with this group, and now we're done with this group. So next we're going to go to the nitrogens, and there's no specific order to this. I'm just going as I see. So for nitrogens, there is a primary amine and a secondary amine. Okay. And just to show you what it looks like, primary amines will look like this. And it's primary because it's bonded to a single carbon. Secondary amines will look like this, where we have a single nitrogen. And sorry, that should not be a 2 or a 3. That should be a 2. Remember, nitrogen wants 3 bonds and 1 lone pair. So we have 1 bond to carbon, 2 bonds to hydrogen, and then lone pair, 2 bonds to 2 methyl groups, and then 1 bond to hydrogen, and then 1 lone pair. So that's what this looks like. And these have a specific marking also on the IR graph. So first I'll just discuss the ranges. So primary amine is around 3,300 to 3,400, and then secondary amine is around 3,000. Okay, but the number again is not important for this group. Same for this group. The shape is important for this group. The number and location relative to 2200 is important for this group. But here, you have to look at how many peaks on the graph it has. Okay, so for example, for primary amine, it's actually going to have 2 peaks per se. So let's say this is 3350. Okay, you will see 2 peaks like that, like fangs. Okay, whereas for secondary amine, let's say 3000 right here. And hold on, let me zoom in. Okay. Okay. So for this, it's at 3000. And all of these numbers, by the way, these are rough numbers. Sometimes they might not be exact because depending on the entire structure, some things can shift to the left or to the right. And you guys will learn about that in the coming lectures. But for now, make sure you understand the primary numbers. Okay. So for secondary amine, it's going to have a single peak. Okay. So to put it simply, they have opposite number of peaks. So secondary amine has 2 peaks, and sorry, primary amine has 2 peaks, secondary amine has 1 peak. Okay, and that's how you distinguish those. Okay, I hope everyone's not confused so far. It should be relatively simple at this point. Okay, so the last important group are carbonyls. And before we get to that, I'm going to need space, so I will erase the left side because we don't really need all this. If I can delete. Okay, yeah, there we go. Okay. So the carbonyls, there's going to be quite a lot, and each of them have slight differences, so it could be very difficult. So just to refresh what a carbonyl is, because some people forget. So it's a carbon and a double bond bonded to an oxygen. Okay. just that. And then usually there are R groups on the side, distinguishing it from like a ketone, aldehydes, etc. Okay, so I'll go through each of them and explain how they look like and what the numbers are. Okay, so first we are going to go, we'll go in order, relatively in order. So the first one is ketone, and ketone is going to have roughly around 1715. And the reason why I say don't pay attention too much to the specific numbers, but it's going to be relatively within the area, is because different resources, sometimes based on like different textbooks, online or in lecture, you might hear different numbers. That's why in lecture they give you like a range, or they show you on the graph. Okay, so but ketone is usually one of the lower number one. Next we have aldehyde, or rather we have carboxylic acid, but so carboxylic acid, the reason why it has a peak here and a peak here is because this is the carbonyl energy peak when it bends right here, and the bending of O to H, that's a different bond, and the bending of C to O, that's a different bond, right? So because these are two sets of different atoms, they have different energy bonds, okay? But I'll still write it down here. Carboxylic acid. So let me write these down and I'll write the numbers later. Aldehyde, Esther, then we have amide. Okay. And then in green, I'll write the values. So carboxylic acid is around 1710. So let me actually put it right here. Okay. Aldehyde is around 1720. Okay, around maybe 1725 is more accurate. And Esther is around 1735. And amide is actually around 1660, but it's also around 33 to 3500. Okay, and the reason being is amide again has a carbonyl peak, but it also has a NH peak. Okay, and if you notice, all the bonds with hydrogens are going to be relatively higher. Okay, same with amines, carboxylic acids, alcohols, and amide is basically a carbonyl with the amine attached to it. That's why it's in this range. Okay, just like carboxylic acid. So I guess I can actually put it right here. Let me shift everything down. So again, Esther is 1735, aldehyde is 1735, 1725, and 1715. Carboxylic acid is both at 1710, as well as 3000 to 3400. And then I'll write the different peaks. carbonyl, carbonyl, alcohol, NH. Hopefully that makes sense, why there are two, and make sure you guys understand both of them. Okay. All right. So these numbers could obviously sometimes be difficult to tell, and honestly, these numbers too, if you ignore these. But these functional groups have these additional peaks. That's why these are easier to see. But for ketone, there's no special thing. But aldehyde and ester do have a special thing, and I'll draw that and explain what I mean. So aldehyde, it has two additional peaks at 27 and 2800. Okay, so two. Let me write it in purple. So aldehyde has two peaks at 2700 and 2800. Okay. So if you see a carbonyl on the graph and it's somewhere around 1720 and you can't exactly tell if it's ketone or an aldehyde, look at 27 and 2800, that area on the graph, and see if it has two peaks. Okay. The peaks should look something like this, like the twin fangs. Okay. And if it does have that, that means that carbonyl is going to be an aldehyde rather than a ketone or an ester. Okay? So that's how you distinguish aldehyde. For ester, it's slightly harder or not as apparent, but it has an overtone. And overtone is basically like a little bump at the very top, and I'll draw what I mean. Okay. So ester has that additional peak to help distinguish it. Now, don't read too much into some of the graphs because they have random bumps, so that might confuse you guys. So ester is honestly pretty hard to tell because the overtone is sometimes confusing to tell whether it's an overtone or not. And ketone, you can distinguish between ester and ketone because ketone is much closer to 1700, whereas ester is much closer to 1750. Again, these are rough numbers. This could be higher or lower, depending on your resource as well as your problem. Okay. All right. So let's take stock at what we learned so far. And so this week we're discussing IR. I talked about broad and spiky kind of peaks. Really, that doesn't really matter. These ones are the broad ones: alcohol, carboxylic acid. Look at the shape. The triple bonds. Look at the location. The amines. Look at the number of peaks. Because even if you know the numbers, you could sometimes get confused between if it's a primary amine or secondary amine. So primary has two, secondary has one, so it's opposite. Okay. And then the bread and butter of like IRs, like these are all the special ones. These are like your standard ones because carbonyls are used a lot in OCHEM and especially in OCHEM 2. So I would really study these differences and study graphs on the unique. So study graphs in practice so you can identify each of the differences. Okay. So next thing we're going to talk about is the ways IR can be shifted either left or right. And these, we're going to call these altercations. Okay, and I'll write it here. Or we'll just call it shifts. Okay. The first one is resonance. Okay. I'll explain what I mean. The second one is going to be ring strain. So let's start with resonance, and we are going to start with a ketone. So a ketone is, let's assume it's 1715. If we give it resonance or conjugation, and that's the word you'll learn later in the semester, but basically having this additional double bond gives it conjugation, which is another way of saying resonance. So we still have a ketone as our functional group, right? We have a carbonyl and we have a C double bond C, but C double bond C, that is going to be in the 1660 range, and we always want to go for the highest function, the functional group in the whole structure that has the highest energy level. Okay, and I'm saying this because that when you're ranking and you see multiple functional groups on a structure, go with the higher energy one. Okay. So here it's the ketone, and that ketone is going to be higher. So, but you won't know exactly how much higher. Okay. All you need to know is that it's going to be higher than 1715. So I'm just going to guess it's at, let's say 1730. Okay. And that might be too much or it might be too little. I'm not sure. You don't need to know exactly this number. Okay. All you need to know is that resonance will increase and shift it to the left. Okay. So in a ranking question, you might get both of these structures, so don't get confused. Ring strain works in a similar fashion. And to explain what ring strain means is you have different number of carbons in a ring. You can have a 3-membered carbon, 4, 5, 6, 7. 6 is obviously the standard one. So I'm going to use a ketone again as an example. And I'm going to scoot over a little bit right here. So again, it's at 1715. Sorry about that. And let me actually zoom in. So 1715, right? So let's say we put that ketone on a ring. Okay. So if we put it on a ring, such as a hexagon or a cyclohexane, these carbons have more strain on them because they are in a ring. Okay, when you try to break those bonds, it's not going to be as easy because it's connected together. Okay, so as a result, that 1715 is going to be, let's say, 1720. Now, if we have less carbons on the ring, like a 4-membered carbon with ketone, it's going to be even worse. It's going to be, let's say, 1740. Okay, again, I'm just making these numbers up, like these two and this one, because you don't need to know the exact number it increases. You just need to understand the concept behind what ring strain and resonance does to the energy levels of the bonds. So as you go lower in the number of carbons in the ring, there is a lot more strain on those bonds. And if you think about it, like if you have 4 friends holding hands, it's harder to get through that versus 6 friends holding hands, and if you're trying to go through that. So that's the conceptual reason around it. But yeah. So these are the shifts, the 2 shifts you have to be concerned with. And that's the rest of the IR material. And again, the whole purpose is to identify, looking at a graph and identifying functional groups, using those peaks and patterns. Okay. And when you add mass spec and NMR, the other 2 spectroscopy things you'll use in the coming weeks, when eventually you'll have to use all 3 to solve a more complicated problem. But for now, I would start practicing how to read graphs and looking at the differences between each of the little mini groups that I've created here. And yeah. So next week we will probably continue with IR, maybe do a refresher, maybe other tips and tricks, as well as maybe solving some problems. And then yeah, each week we'll just do whatever you guys cover in the past week. So eventually we'll cover mass spec 1 week, NMR. NMR will probably take us 2 weeks because NMR is usually the hardest for students, and it also takes a lot more explaining and it's slightly more complicated than IR and mass spec. And then we'll have a week before the exam, and then after the exam we'll talk about the next unit. Okay, so that's how this semester is going to go. If you've been to my previous weekly reviews of previous semesters, you should know how this works. Obviously, if you want to join live, you can, Mondays at 4 p.m. using e-learning, or you can use YouTube to view this recording later. And that's probably where you're watching right now. But until next week, I will see you guys later. Bye.